Okay, so the plan for today is we're actually gonna not do 4.2 today. The plan for today is to start chapter 4, fractions. And today we're really just mostly working on visualizing fractions and introducing the ideas associated with fractions. So we're gonna kind of take an easy entry into fractions. I know that this is a topic that a lot of folks kind of, find challenging and maybe even a little bit scary, but hopefully, as we go through it and we start to think of it, visually and so on, hopefully it'll make a little more sense maybe than it has in the past. And if you're good with fractions, like, congratulations, you're already ahead of the game. But, this is definitely, I think, where the course tends to take, become a little more challenging, let's say. Um, Note that we have the Unit 1 exam this week, so just remember to complete that. We talked quite a bit about the details already. But again, just remember not to wait until the last minute to take the exam. I recommend planning to take it no later than this evening. And the quote of the day today is that difficulty tends to increase non-linearly with complexity. So if you have, whether maybe it's a math problem or something complicated in life, if you like double the complexity of something, it's probably a lot more than twice as difficult to manage. Um, so as kind of a general rule, if we're starting in a certain level of complexity and we realize that in the future things are going to get more complicated for some reason, maybe we're, moving across the country or to another country, or maybe starting a new job or anything like that. Um, if we allow all of that complexity to come into play and then try to sort it out later, it's probably going to be a lot more difficult to sort out on the back end than if we start to reduce complexity leading into that. And then whenever that additional, complication in our life hits, we'll be kind of situated a little better to handle it. So we see that a lot in math. We always like to, take one step, maybe one equation solving step, and then simplify everything as much as possible before we take another step. I don't want to take 4 steps at a time. I want to take one step, it becomes a little more complex, and then I simplify everything. I make it as simple as I can. I get rid of as much complexity as I can. Then I take one. Oh, somebody said they can't hear me. Can anybody else hear me? Can anybody else not hear me? Okay, so yeah, if you can't hear me, it could be that your microphone or that your sound is down. So just check that. Uh, so yeah, that could be. I've definitely done that before. I've been in like Zoom meetings. I'm like, wait, I can't hear anything. Is my oh yeah, yeah. And if that doesn't work, if your sound is up, then you can log off, log back in. Sometimes that will fix it. Um, or definitely if you have like earbuds or whatever. Okay, looks like it's fixed. Um, but yeah, so in math problems, we like to try to decrease complexity before we do another step that adds more complications into the mix. I think this is, true in general in math problems. And, certainly when we're doing things with several steps, we don't want to take a bunch of steps and then simplify. We want to try to simplify at the end of each step. Okay, so moving on to fractions. So again, fractions is kind of, I feel like most courses have like an over the hump kind of topic, that it's kind of like, it's the topic that's the most challenging one in the course, kind of the crux of the course. And, if you put in the time, if you put in the energy, if you drill those problems, and you make it over that hump, the rest of the course is kind of downhill, like in a good sense, and that it's, a bit easier. Uh, but if you don't put in the time for that difficult section, then the rest of the course is kind of a slog, because it's like there's a fundamental something fundamental that you're not really understanding well, and it's going to pop up in future sections quite often. So I think fractions is that topic in our course here. So I would recommend, kind of like I mentioned earlier in the course with like the times tables, that was maybe another like mini hump to get over. If you drill your times tables a couple times a day, um, over a week or two, like you just start to recognize them and you get over that hump and then you're good after that. And I think fractions is a little bit like that. A lot of people just have kind of a natural aversion to fractions. Maybe they've struggled with it in the past. Um, but if you kind of meet that head on instead of shying away from it and you do a little bit of work several times a day, maybe morning, afternoon, evening, do a 10-minute session where you work through some problems or something, that's much better than trying to sit down at like Sunday at 8 p.m. and work through, 30 problems. That just kind of reinforces that like, oh, I can't do it kind of mentality because if I sat down to do 30 problems, by the time I got to problem 15, I'd be kind of, a little bit worn out. And by the time I got to problem 25, I'd probably be making mistakes. Um, but if you sit down and you take it a little bit at a time, you're kind of fresh going into it. You're probably a little bit, less aggravated going into it. I mean, who wants to sit down and spend 3 hours doing, math problems on a weekend or something? It's a lot more manageable to sit down and do 10-minute chunks here and there. And it's also better for learning. Like if you learn in little chunks, you learn a little bit today, you go to sleep, that kind of somehow gets, magically turned into long-term memory and you kind of synthesize things a little better. You wake up tomorrow, you learn a little bit more. Your brain works a lot better that way than trying to learn in some huge chunk. You really just can't process that, over one night. Okay. So what is the idea? Well, the idea is that a fraction is simply a part of a whole. So if I look at this example here, I have one whole pizza, and I can cut it down the middle, and I'm certainly not an artist, so I can cut it down the middle, and I have one half of a pizza and another half of a pizza. So what does this fraction signify? One half, say for instance, this slice of pizza, that signifies the denominator 2 signifies the number of slices the whole is divided into, and the number 1 signifies the number of slices, let's just say something like that you have. Right, so if I have this slice of pizza on my plate, the entire pizza was cut in 2 pieces. That's what the 2 signifies. And I have one of those pieces in my possession or on my plate or that belongs to me. If the entire pizza was cut in 2, there's another 1/2 slice pizza, and that can go to somebody else, right? I could take that same pizza and cut it a bunch of different ways. I could cut it into 12ths, right? So maybe this slice of pizza is 1/12. This pizza was cut into 12 equal size pizzas, equal size pieces, and I have one of them. I could look at, say a pizza that was cut into 13 slices. So this is 13 slices. And maybe I have 1, 2, 3 of those slices that belong to me. It could be these 3, right? It could be that one, this one, and this one. These slices are all kind of interchangeable from our perspective anyway. So if I had 3 slices, maybe I just make it these 3. And I see that this region, maybe I'll outline it in red. This region is made up of slices that are each 1/13 the size of a pizza. It's this whole pizza was cut into 13 slices. And here I have three of them. 1, 2, 3. So my denominator is simply how many slices I've cut a whole pizza into, and my numerator represents how many of those slices I have. Right, I know that I can, for instance, take a pizza that's cut this way in half. I could come along and cut it again this way. If I cut it a second time this way, then I would have 1, 2, 3, 4 pieces that whole pizza was cut into. So these would represent fourths. And this kind of top left piece would be, say, 1/4 of the pizza. This bottom left piece would be 1/4 of the pizza. And I see that's in combination the same as 1/2 of a pizza. So I could think of, for instance, 1/4 plus 1/4 being the same as 1/2. If I have two slices that are quarter slices of pizza, that's equivalent to getting one slice of pizza that's a half a pizza. So I can change the way that my fractions look by just slicing my pizza more times or fewer times or slightly differently. So I see that if I have 1/4 plus 1/4, that gives me a half. Or if I have a thing plus itself, I just have two of that, right? So I could also say that like 2/4 equals 1/2. I could think of it this way as well. I have 1, 2 1/4 slices of pizza that put together make the same amount of pizza as 1/2, as one slice of a pizza cut in two. So 2 slices of a pizza cut in 4 is the same as one slice of a pizza cut in 2. Or this would be the same as, for instance, 4 slices of a pizza cut in 8ths, cut 8 ways. If I cut like this and like that as well, right? So I would have 1, 2, 3, 4 slices of pizza that I would have, and my pizza as a whole would be cut into 8 pieces. So I'd have 4/8, right? That would be the same as 2/4, the same as 1/2. I can change the way that my fraction looks by just taking the same amount of pizza, but cutting it more times or cutting it fewer times or cutting it differently. So that's a really important idea in fractions, right? It underlies this, really a lot of the ideas in fractions. For instance, we might see 1/4 plus 1/4, and we might be tempted to like add the numerators and add the denominators to get something like 2/8. But we see that 1/4 plus 1/4, I mean, that's certainly not 2/8. 2/8 would be a much smaller amount of pizza than 1/4 plus 1/4 or 2/4. So this is all stuff that we haven't gotten to yet as far as the math goes, but my point is that by thinking of this model like pizza or parts of a whole, if we always think back to this to kind of reasonability check what we're about to do, I think that's a very useful thing to do. So when we start talking about adding fractions or multiplying fractions or making equivalent fractions, this is what we're going to think about is we're maybe changing the way that we are slicing up the pizza, or maybe we're accumulating more slices of pizza or losing slices of pizza, something like that. We can move away from the pizza model because, I'm not an artist, so we can look more at abstract diagrams like this. So we could look at an example like this one here, where I have just a circle. I can count how many slices this circle is divided into. 1, 2, 3, 4, 5, 6, 7, 8. I see this circle is split into 8 slices. And how many of those slices are shaded? 1, 2, 3, 4, 5. So the shaded portion here represents 5/8. The entire circle is split into 8 equal sized slices, and the shaded portion is 5 of those slices. So I could think of parts of a circle. Sometimes it's also a little nicer to think of like a block diagram, kind of like this. I have like a whole square or a whole rectangle, whatever it may be, that's split into 1, 2, 3, 4, 5, 6, 7, 8, 9 component squares. So this is split into ninths, as we would say. And I have 1, 2 of those that are shaded in. So the shaded portion represents 2/9 of the entire square or rectangle of this entire figure. Okay, so let's take a look at some different fractions here and let's try to model them with either a circle or a rectangular model. Okay, so if I look at 1/3, so I have a circle, the 3 on the bottom tells me that I'm going to split this circle into 3 equal sized parts. So it looks kind of like that. Looks a little bit like a Mercedes symbol. And the 1 in the numerator tells me that I want to select one of those parts, or I want to shade in one of those parts. It doesn't matter which one I pick. I'll go with this one. And this would be a model for 1/3. You could have picked this one instead or that one instead. Those are equally valid options. If I have, say, 2/5, again, the denominator, the 5 here, tells me how many pieces to slice my circle into. I want it to look roughly equally sized. It's not going to be perfect, of course, but it should be reasonably equal. It shouldn't be like, this. We don't want something like that. That's uh, a little too different. It's going to throw off our intuition, but something like this, close enough. And I want to shade in, I want to select 2 of these bits. I could do something like this. There's nothing wrong with that. Usually though, if I'm free to pick which ones to shade in, I'll pick adjacent slices. So now I see that I can think of 2/5 as like this slice and that slice combined, or I could think of it as kind of this whole bigger wedge representing 2/5. If I have something like 7/10, again, I could draw a circle and use that as a model. That's perfectly fine. I could also use blocks. If I look at 10, I mean, I guess I could just make like a long rod of 10 blocks, roughly equal size. So this gives me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 blocks, and I would shade in 7 of them. Technically, it doesn't matter which 7 you pick, but again, I would choose adjacent ones. I would probably also choose like, to shade one starting at the left. That's probably just going to be a little bit cleaner if I need to actually do anything with this model. Another thing I noticed though is just like the 9 blocks up here, sometimes it can be a little nicer, a little quicker and easier to count if you put these in a grid. So if I think of 10, its prime factorization is 5 times 2. I can make 10 blocks this way, right? Uh, 5 columns and 2 rows. And I could shade 7 of these. Either of these would be valid models, or of course I could draw a circle, split into 10 roughly equal sectors, shade in 7 of them. Lots of ways to think about this model. But if I were to draw a bar like this, when I think of the entire bar, I'm thinking of this as representing one unit. So 7/10, I take that 1 unit, I split it into 10 subunits and select 7 of them. Or I'm thinking of this entire rectangle as 1 unit. Or I'm thinking of, say, this entire circle as representing 1 unit. When I divide that circle up, then I can select parts of a whole, parts of that 1 unit. So let's look at our first property for fractions, the property of 1. And this property says simply, let me actually zoom this in a little bit, make it a little easier for you to see. This says simply that any number that's not 0 divided by itself equals 1. If my numerator and denominator are the same non-zero number, the answer is 1. Well, why is that? What is a over a representing? Well, if I think in terms of my circle diagrams or block diagrams, really what I'm saying is take a circle. This whole circle represents 1. Divide it into a equal size slices. Maybe just for illustration, I'll divide it into 3 equal size slices. How many of those slices should I select? I should select a of them. In other words, I should select all of them. I should shade in all of the slices that I made. Well, that just shades in the entire thing. Or if I did the same thing with, say, a rectangle or a square, this entire square here represents 1. If I divided this up, maybe I'll just divide it into 9 as an illustration. So if A was 9, I'm dividing this into 9 sub blocks. And then how many am I selecting? If I have 9 over 9, I'm selecting all 9. Right? So 9/9 equals 1, or 3/3 equals 1, or 4/4 equals 1, etc. So the denominator tells me I take a whole, either a circle that I think of as representing 1, or a rectangle or square that I think of as representing 1, something like that. I take a whole. The denominator, the bottom number, tells me how many times to cut that up, how many slices to make. And the numerator tells me how many slices to select. If I select all of the slices that I made, then I just have the entire whole. I just have 1. And as an aside, we can go either way with this, right? We can either say that if I have 3/3, I can rewrite that as 1. But also, if I have the number 1, I can choose to think of 1 as 3/3, or as 4/4, or as 8/8. Sometimes that will be a helpful property for me. So I'll choose to think of 1 in a creative way. Maybe in one context, thinking of the number 1 as 5/5 is actually really helpful. Maybe in another context, thinking of it as 7/7 is really helpful. So we have an equivalent fractions property that if I have a over b, that's equal to a times c over b times c, again for b and c not 0. Remember back when we started talking about division, we said we don't want to divide by 0, right? So we always have these little special cases that make sure we don't divide by 0. not special cases, these constraints that make sure we don't divide by 0. What's kind of the idea here? Let's illustrate this with maybe 1/3. So here, b equals 3 and a equals 1. So I have my whole, my 1 unit. I split it into 3 equal size slices. That's what the denominator, the bottom number tells me to do. And then I select one of those. That's what my numerator, the top number, tells me to do. It tells me how many of these I'm selecting. Now let's take c equals 2. So I'm saying that 1/3 is the same as 1 times 2 over 3 times 2, or 2/6. C equals 2 says take each individual slice and split it in 2. So I'll take this kind of top left slice and I'll cut it in half. I'll take the top right slice and cut it in half. I'll take the bottom slice and cut it in half. Well, I now have 6 total slices. There's 1, 2, 3, 4, 5, and 6. Equal sized. I mean, I'm not a great artist, so they don't look super equal sized, but we're imagining they are equally sized. And I have now actually 1 and 2 of those slices selected, because the original bigger slice I selected got cut in half. So now I have 2 of the new smaller slices that I've selected. If I multiply the numerator and denominator by the same number, I end up with the same fraction. That's what we call an equivalent fractions property. And I can go either direction. When we go left to right, we say that maybe something like 1/3 equals 2/6. Sometimes that's super helpful because maybe I want to work with this fraction in a way where I think of slices of size 1/6 instead of slices of size 1/3. Maybe that works a little better, right? If I have 2 plates of pizza and one plate of pizza has a slice of size 1/3 on it, and another plate of pizza has a slice of size 1/6. If I put those two together, how much pizza do I have? I might not be very sure. I have like a 1/6 plus 1/3, but I realize that I can cut that 1/3 slice in half and make 2 1/6 slices, and that can combine a little nicer with the other 1/6 slice. Again, a little more advanced than where we're at now, but just giving you a little bit of a preview of where this might be used. Note that we can also go the other direction. Since I've scribbled all over this one, let me just draw a fresh example here. I could go the other direction. Just for the sake of variety, let's say that we have eighths here. And let's suppose that I'm in a situation where I have 2/8. So I have 2/8. But I kind of recognize that I could think about this in terms of fourths instead. And then I would just have 1/4. So for my model, I can see that 2/8 equals 1/4 by just kind of gluing together a couple of slices instead of before we cut them apart. What does gluing together slices look like? Well, I would take my 2/8 and I would recognize, oh wait, well, 2 is 1 times 2, and 8 is 4 times 2. I can find a common factor, as we call it, that's in the numerator and denominator, and I have this equivalent fractions property that says I can go this way as well. A times C over B times C equals a divided by b. A lot of times we just call that dividing out a factor. Again, maybe a little more advanced than where we're at now. We're going to talk about this extensively throughout the next few sections, but just giving you kind of a taste of what's coming up. So by our equivalent fractions property going from the right to the left side, 1 times 2 divided by 4 times 2 is just 1 divided by 4. We see that pictorially with our model, and we see that using our property here. As always, we kind of start with a model to get some gut feeling, some intuition. But if I had, whatever, 42 over 76, I don't want to draw a circle with 76 slices and 42 slices filled in. Like, that's going to take forever, right? I want something that's going to generalize a little better to problems with larger numbers. And for instance, here I would see that 42 is 21 times 2, and 76 is 38 times 2. And I see that I could, again, do the same kind of thing. I didn't have to draw a picture. I was able to lean directly on the algebraic property. Okay. So for this example, for each of these fractions, let's find 3 equivalent fractions. How do we find equivalent fractions? Well, we pick a number c that's not 0, and we multiply both the top and the bottom by that number. So 1/4 is the fraction I'm starting with here. Maybe if I pick c equals 2, then I get 1 times 2 over 4 times 2, or 2/8. 2/8 would be an equivalent fraction to 1/4. If I were to pick, say, c equals 3, 1 times 3 over 4 times 3, well, that's going to be 3 divided by 12. So 1/4, 2/8, 3/12. Maybe I could pick c equals 10. 10 is usually an easy number to multiply by. And as long as I multiply on both the top and the bottom, my fraction stays the same. 10 divided by 40. All of these fractions, all of these 4 circle fractions, represent the same quantity, the same number, just written in different forms. The same way that we say 1 plus 1 equals 2, I could think of the quantity 2 as being 2, or I could think of it as 1 plus 1, or I could think of it in different forms. Same kind of idea here. I could think of the quantity 1/4 representing a certain amount of pizza. If I took a whole pizza, cut it into slices, into 4 equal slices, and I had one of them, that's the same amount of pizza as if I had cut it into 8 equal slices and have 2 of them, or I cut it into 12 equal slices and have 3, or had cut it into 40 equal slices and have 10, etc. Okay, if we think of something like 3/8, again, I can pick different numbers for c, can pick them however I like, but I'll probably, choose ones that are fairly easy to multiply by. I'll pick different numbers for c, like maybe 2, for instance. That's a pretty good one to pick. I can get an equivalent fraction by multiplying by 2 on both the top and the bottom, the numerator and the denominator. And I see that this is 6 divided by 16. If I pick c equals 3, again, I'm picking that because it's an easy one to multiply by. I multiply by 3 in both the numerator and the denominator, the top and the bottom. 9 divided by 24. Or if I pick maybe c equals 5, 15 divided by 40. These are all equivalent fractions. These all represent the same number. These are all equal to one another, is another way to say that. 3/8 is the same as 6/16. 3/8 equals 6/16, which equals 9/24, which equals 15/40, and so on. And if we look at 2/7, again, we could do a similar thing. Pick some different values of c, maybe c equals 10. So 2/7 equals 20/70ths. If c equals 100, those first two fractions are also equal to 200 divided by 700. If c is 1,000, 2,000 over 7,000, right? We can find lots and lots and lots of equivalent fractions just by picking different numbers c to multiply by, and then making sure that we multiply in both the numerator and denominator, the top and bottom. Any questions so far on this? Okay, a couple definitions. So mixed numbers. Oh. So what are mixed numbers? Mixed numbers are numbers written in this notation, something like 1 with a fraction, say something like 2/3, immediately next to it. So something like 1 2/3, you might have, been making a recipe at some point and it called for 1 2/3 cups of flour or something, and this is how it might have been written. So a mixed number is something like this, where we have a natural number and immediately next to it a fraction that's a ratio of two natural numbers. I think your book says actually whole numbers, but like you never write like 0 2/3, or you wouldn't write like 1 0/3 because that's just 1. 0 2/3 is just 2/3, and you can't divide by 0. So I don't know why they have whole numbers in there instead of natural numbers. I would say natural numbers is more accurate. One kind of somewhat unfortunate thing about this notation is almost always in math, when we omit the explicit operation, like if I have 3x, I mean 3 times x, right? Or if I have like a 4 next to a 3 in parentheses, that's 4 times 3 or 12. Almost always when we omit the operation, it implies multiplication. Unfortunately, mixed numbers, when we omit the operation, it implies addition. So if I say I want 1 2/3 cups of flour, I don't mean one amount of 2/3 cups of flour. I don't mean to multiply them. I mean, get a cup of flour, put that in, and then get another 2/3 of a cup of flour and put that in. We haven't gotten to decimals yet, but I think most of us are pretty familiar with decimals. We've seen them around, at least in dollars and cents and so on. It's a little bit like, 1.75 or something like that, where we have like a whole and a part of a whole that are kind of like smushed right next to one another. It's a little bit like that kind of idea, where I have like a whole part and a fractional part that are just kind of smushed together. Personally, mixed numbers kind of irk me because it's like, why is it that everywhere else that we omit the operation, it's multiplication, but here for some strange reason we make it addition? But I'm not the one who gets to decide what the mathematical notation is. Somewhat strangely, there's actually like really no one that decides what the mathematical notation is. There's not like a math dictionary that's like that this notation means this thing and everybody agrees on it. It's just kind of like all of the textbooks and all of the people kind of agree on what certain things mean, and somehow that just works. So it's kind of really interesting. You think that there would be like a governing body who would like decide what notation is valid and what's not valid, but there really isn't. So it's really it's a really interesting linguistic phenomenon, mathematical notation. But anyway, so this is what mixed numbers look like. And I think the easiest way to think of these is like, cups of flour in a recipe or something. That's something that most folks are familiar with. We could also look at fractions just like a over b, and we might realize that there are a couple different forms of fractions that we can consider. We can consider fractions where the numerator is less than the denominator, like 3/5 or 1/4, something like that. Where if I look at my model, I don't have a whole pizza, on my plate, so to speak, or I don't have a whole rectangle or square. Or I could look at an improper fraction where the numerator is at least as big as the denominator. Something like 5/3. Well, I actually have 1, 2, 3. I actually run out of thirds with just one circle. If I have one circle, I divide it into thirds. I have 3/3 that I could potentially shade in. I shade in all three of those. 1, 2, 3, but I need more. I need 5 of them. So I actually need to make a new circle. Here's number 4 and number 5. So an improper fraction is one where, kind of in a sense, we could split off a whole number bit from our fractional bit, but we've chosen not to. Now I, I think there's a lot of sentiment for whatever reason in like high school math and even grade school math that it's somehow like immoral or something to have an improper fraction or to have like a radical in a denominator or these kind of things. And personally, I think that's kind of silly, right? There are times that mixed numbers serve us better. There are times that improper fractions serve us better. So, if I have 5/3, I can see pictorially that this is the same as the mixed number 1 and 2/3. It's one whole that I filled in, one whole pizza here, and then another 2/3. Sometimes improper fractions, in fact, a lot of the time, I would argue improper fractions are actually nicer to work with than mixed numbers. So there's nothing like immoral or bad or fundamentally bad about an improper fraction, even though it's called improper. Um, in fact, a lot of the times they're nicer to work with. Most of the time when I'm teaching higher level courses like statistics or calculus or anything like that, if we get an improper fraction, we just leave it that way because it's much easier to work with in a lot of contexts. Now, if I want to graph it, if I want to put it on a number line, most of the time it's easier to switch it over to a mixed number because I know that 1 and 2/3 is it's like more than 1 cup of flour, but not quite 2 cups of flour. I know that it's going to lie between 1 and 2 on a number line. So it's easier for me to locate or to tell what the size of the fraction is, or to order it with other fractions, which one's bigger. That's usually easier when I have a mixed number. So if I'm ordering or graphing on a number line or something like mixed number is going to be a little easier. But if I'm actually working with the fraction, doing computations with it, adding it to other fractions or subtracting it from them or multiplying it by them, having an improper fraction is much nicer, almost universally. Okay, any questions so far? All right, let's go through some exercises. Let's look at these depictions of fractions. And these will all be improper fractions. We'll name the improper fraction, and then we'll rewrite it as a mixed number, just like we did up here with this one. Okay, so what do I have here? Well, I have one circle completely filled in. And then over here, I have 1, 2, 3, 4, 5, 6, 7, 8. As kind of a little side note, I can use symmetry in these problems. I notice that I have a perfectly straight line going top to bottom. So I have the same number of slices on the left as I have on the right. I also noticed that I have from just the right side a perfectly straight line going across. So I have the same number of slices above as I have below. So I have two slices above, another two below. That makes four, and another four on the other side. I know that this has got to be 8 slices. I don't have to go around and label every one. But I do have to find a perfectly straight line like that. If it's, kind of off to the side like this, even if it's close to being straight, then then I would just have to count them. So I see that I have my my hole here, my pizza, so to speak, divided into 8 slices, and I have one of those. So this represents 1/8. So I have one hole plus 1/8, or that's 1 and 1/8, the mixed number. I have something similar here. I have one hole. Let me write that a little further over to the left so it doesn't get confused with the other block. I have one hole, one entire square shaded in. And then this square over here on the right has 1, 2, 3, 4 blocks. And I've shaded in one of them. So this represents 1/4. The hole was divided into 4 slices, and I have shaded in one of them. So I could think of this as being like 1 plus 1/4, or just written as a mixed number, it's just 1 and 1/4. We would just say this is 1 and 1/4. And similarly down here, I see that, again, I have one whole block shaded in. And my second block it's split up into sub blocks of 9 sub blocks, 1/9 each. And I have 2 of those. So 1 and 2/9. Or this problem, I had to kind of rig this up. So these are all supposed to go together. So all of these together, what would this give us? So I have one hole here, one hole here. Here I have, well, this circle is split into slices, into 8 slices. So I have eighths. And I have 1, 2, 3/8. And then I have another 3/8, right? So if I think of just moving these slices up here, this would shade in 1, 2, 3 more. So this would actually be a total of 6/8 combined between these two. I could just move slices to a more convenient location if I would like. There's nothing wrong with that. If I have 2 plates that each have 3 1/8 slices of pizza, I could just kind of slide them all over onto one plate and smush them together. Or I see that 1 plus 1 is 2 and 6/8. What if I had even another? Let me erase all of this. What if I even had another one of these? I would love to like put this over here, but OneNote doesn't let me move things around that easily. So what if I had all of these together that I wanted to describe in an improper fraction or a mixed number? So I see I still have one hole and one hole. I can think of maybe moving these 3 up to here. I still have some extra room in here. I could move this one, say, up to here. I've still got some extra room on this like pizza plate. I can move this one as well. I've actually glued a bunch of pieces together, and actually constructed a complete nether hole. And then I'm left with this kind of vestigial 1/8, this slice of pizza that doesn't really fit in with any of the others. So this would be like 3 and 1/8, right? This is leveraging my A over A equals 1 kind of idea. I have 8 slices that I've glued together to make just one whole pizza. And that gives me 3 whole pizzas now. And then I still have this 1/8 slice that doesn't really kind of fit in anywhere else. So it just sits there as a 1/8. Now, something to note is I could have written all of these as improper fractions as well. I could have chosen to say count this as 8/8, this as 1/8, and then I'd have had, well, what? 8/8 plus 1/8, that would give me 9/8. I would have 9 slices, each of size 1/8. This clearly represents the same amount of pizza, right? Or I could have written this as 1, 2, 3, 4, 5, 5/4. Or I could have looked at this as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11/9. Or even down here, I could have looked at this as, well, here's 1 through 8, 9 through 16, 17, 18, 19, 20, 21, 22, 23, 24, 25/8. So 3 and 1/8, 25/8. They represent the same idea, the same quantity, the same number, just written in different forms. Anytime that I have an improper fraction, that means my numerator is bigger than the denominator. That means that I have more slices than I've sliced a single pizza into. That means I can always pull off a single pizza. That means I can always, convert that improper fraction into a mixed number. If I have a proper fraction, say just a number like 3/8, there's not any whole pizzas there to pull off as a whole number in front. A proper fraction just kind of pretty much has to stay a proper fraction. We might be able to make it into an equivalent fraction, 3/8 or 6/16 or something like that. But it has to stay a proper fraction. It can't turn into a mixed number because there are no holes to pull off and write out in front. But an improper fraction can be converted to a mixed number. Now, again, is it better to work with the improper fraction or the mixed number? A lot of times it's better to work with an improper fraction. But is it intuitively easier to understand one versus the other? Well, the mixed number is intuitively easy to understand. We know that 3/8 is a little bigger than 3, but not quite 4. So we know it's between 3 and 4. That gives us an idea of the size, right? If I want 3 and 1/8 cups of flour, I'm probably going to pull out the 1 cup measuring cup, do 3 of those, and then get the 1/8 out and do 1 of those. I don't want to get the 1/8 out and do 25 scoops of, an eighth a cup of flour. Like that's going to take forever. So intuitively speaking, or practically speaking, a lot of times mixed number is nicer. When working with the fraction in mathematical calculations, a lot of times the improper fraction is nicer. We want to be able to think in both contexts and to go back and forth as needed. Okay, so we looked at the relationship between mixed numbers and improper fractions in this model, in the slices of circles or the squares model. But again, if I have a much bigger number, even something like this, 25/8, this would be pretty cumbersome to write out. Can I come up with a strategy, an algorithm, a process that uses some of the mathematical tools that we've already created to do this work when the numbers are more cumbersome or a little less easy to work with. Can I take each of these improper fractions, 3 halves, the numerator 3 is bigger than the denominator 2, 13 fifths, 13 is bigger than 5, 42 thirteenths, 42 is bigger than 13. These are all improper fractions. Can I convert them into mixed numbers, right? So if I know that I need 13 fifths cups of flour, not that anybody would write their recipe in fifths of cups of flour, but whatever. I don't want to sit here doing 1, 2, 3, all the way up to 13. I'll probably lose count and get too much or too little flour in there. I want some whole cups of flour plus some extra, maybe 1 or 2 extra fractional cups, something like that. So how do I do this? Well, I note that if I do 3 divided by 2, long division isn't the best here, but I know that I get 2 goes into 3 is 1, 1 times 2 is 2, with 1 left over. In other words, 3 halves, I can think of this instead of a fraction, I can think of it like it was a division problem, right? This same notation we use to represent division, right? Like, 18 over 3 equals 6. This is a problem we might have seen in the last chapter or an earlier chapter. So 3 halves is what? It's 1 with a remainder of 1. This is how we'd have written it before, and just that looks like absolute value of r or something. But this is 1 with a remainder of 1 to be clear exactly what I mean there. Let's get rid of the 18 thirds. That has nothing to do with this other than just showing that the notation for a fraction is just the same notation for doing the division problem. So 3 halves is 1 with a remainder of 1. But really, this remainder of 1, this is telling us how many halves are left over that weren't able to be kind of put together into a whole. Or in other words, it's 1 with a remainder of like 1/2. But we don't want to write it this way. I mean, when we say remainder of 1, I mean how many parts of the whole are left over. So I just write it as 1/2. So 1 plus 1 divided by 2, or just 1.5. So this idea of converting an improper fraction into a mixed number is really just saying do the division, get number with a remainder of other number. The number in front of the remainder, the kind of whole number part that we pulled off, that just kind of sticks around. And then what do we do with the remainder? It becomes the numerator. In the original denominator, the number of ways the pizza was originally sliced, that hasn't changed. That just goes in the denominator. And that's our fractional component of the mixed number. Or if I look at 13 fifths, well, I see that 5 goes into 13 twice. 2 times 5 is 10. This gives me a remainder of 3. Or 13 fifths is 2. And 3 fifths. We didn't change how we're slicing the pizza. It's still sliced into fifths. Each slice is size 1/5. That denominator just kind of comes down. The 2 with a remainder of 3, the 2 is the whole number part of the mixed number, and the 3 is the numerator of the fractional part. That's the number of extra slices that we have left over that can't be combined with other slices to make another whole pizza. Or something like 42 over 13, slightly bigger numbers. I wouldn't want to write these all out in terms of, circles and slices of size 1/13 or, uh, lines of blocks that are 13 blocks long and start shading until I get 42 of them. I wouldn't want to do that. But I see the 13 Well, 13 times 1 is 13, times 2 is 26, times 3 is 39, and times 4, well, that's too much, right? So 42 over 13 is 3. That accounts for 39 of my slices, with a remainder of 3. 39, 40, 41, 42. I have 3 slices left over. Or this is 3 and 3/13. 3 the 3 whole pizzas that I was able to make by gluing a bunch of these 42 slices together. Then I'm left with 3 vestigial slices, 3 that are left over that I can't combine with anything else anymore to make other whole pizzas. Each one of those is of size 1/13 of a pizza. So 3 and 3/13. Any questions on that? Okay, now let's look at going the other direction. If we have a mixed number, can we convert it into a proper fraction? What's the basic idea here? Something like 1 2/3. I have one whole pizza, and then I have 2/3 of a pizza. I'll have a pizza divided into 3 equal sized slices, and I shade in 2 of those. This pizza is cut into thirds. It's cut into 3 equal sized slices. Let me choose to take my whole pizza here and cut it into 3 equal sized slices. How many slices do I have? 1, 2, 3, 4, 5. Or I can really think of like 1 plus 2/3. I can think of 1 as 3/3, right? Right. A over A equals 1, 3/3 equals 1. I could convert 3/3 into 1. That's kind of what I did up here. Not with thirds necessarily, but I could go the other direction. I could take whole pizzas and slice them up into whatever size pieces I want. I can choose to think of this first pizza, instead of being amount 1, I could think of it as 3/3. 3 slices, each of size 1/3 of a pizza. And when I aggregate these together, I have 3 slices and 2 more slices of the same size. This gives me 5/3. So where did this come from? What was really the process? I take my whole number and I multiply it by what I want the denominator to be. Why is that? Well, I decide what I want the denominator to be. I need that same factor in the numerator so that I get A over A equals 1, for instance. If I have something like 2 and 1/4, it's going to be a similar process. I have 2 whole pizzas. And then plus a quarter of a pizza. So this is 2 pizzas. But again, I can choose to, because I want these slices to mesh with this extra 1/4 over here, I can choose to cut these 2 pizzas each into 4 slices of size 1/4. How many of these 1/4 slices do I have? Well, I have 2 times 4 slices for each pizza. Or this is 8/4. 2 is the same as 8/4. And then I tack another 1/4 onto it. I have 9 slices, each of which is 1/4 of a pizza. So practically speaking, if I have a mixed number, like 2 and 1/4, I multiply denominator times whole number. I add numerator. 4 times 2 is 8. plus 1, and I keep the same denominator. I haven't changed my kind of fundamental way that I slice the pizza. It's everything is still in terms of quarter slices. Or if I have 1 2/3, I take 3 times 1 plus 2. 3 times 1 is 3, plus 2 is 5. And that's the number of slices of size 1/3 that I have. So if I have 3 4/7, I'd rather not draw this out. That's a lot of drawing and slicing and all that. But the same model works. What does 3 4/7 turn into as an improper fraction? I multiply denominator times whole number. This is saying for each of these 3 pizzas, these 3 whole pizzas, I want to split them into, I want to cut them into 7 equal slices for each of those. That's going to give me 7 times 3 or 21 slices made out of those 3 whole pizzas. And then I have 4 extra slices of size 1/7 sitting off to the side that I need to account for as well. 7 3s are 21, plus 4 is 25. What size are all of these slices now? 1/7 of a pizza. Are there any questions on anything so far? So I know fractions are, like I said, a little bit scary, a little bit of an uphill climb, but I think starting off like this, starting off with all the way back up here, there we go. Starting off with thinking of it as a part of a whole and always coming back to that, right? Always coming back to fundamentally, what does the top and the bottom number mean? What does the numerator and denominator mean? The denominator is how many times we slice the pizza, how many slices we slice it into, and the numerator is how many of those slices we have. We can change the way that we slice the pizza. We can slice it more times or fewer times, and we can come up with equivalent fractions that represent the same amount of pizza, just sliced differently. This, again, property of 1, super important to be able to use in both directions. We've seen that. We can come up with equivalent fractions by multiplying numerator and denominator by the same non-zero number. And we have this important idea of being able to switch back and forth between mixed numbers and proper and improper fractions. So we've actually gotten through a lot of material today. Let's do one more example to kind of summarize what we've worked on, and then we'll call it a day for today. So here I have a list of numbers. Some are proper fractions, some positive, some negative. Some are mixed numbers, some are improper fractions. So let's write these in order from smallest to largest. And then let's also plot on a number line. Well, the first thing I know is that any negative number is less than any positive number. Now, something we need to be a little careful about. What is a negative mixed number? Like negative 1 2/3. This is negative of the mixed number 1 2/3, just to be clear. It's not like negative 1 plus 2/3. It's like negative 1 and then go another 2/3 to the left. So this is negative of 1 2/3. So if here's 0, I know that negative 3/4, negative 1 2/3, and negative 5/2 are all going to be to the left of 0. And I know that the positive numbers in the list, 3/4, 1 2/3, and 5/2 are all going to be to the right of 0. So that's the first thing I do. I split apart my negatives and positives. That just makes it easier for me to look at each of these individually. Now, do I want to look at these in terms of mixed numbers or in terms of fractions and improper fractions? If I convert the 1 2/3 to an improper fraction, Well, what do I have? 3 times 1 is 3, plus 2 is 5, 5/3. How does 3/4, 5/3, and 5/2 compare to one another? That's kind of tough to look at and decide, right? This is actually a situation where I'd much rather work with the mixed number version. 1 2/3, I know this is between 1 and 2 on a number line. 3/4, that's a proper fraction. That's less than a whole, right? I have 4 slices and I've only filled in 3. I don't even have 1. This is between 0 and 1 on a number line. Now 5/2, I'm actually going to convert this into a mixed number. I know that 5 divided by 2 is 2 with a remainder of 1. 2 times 2 is 4, plus 1 is 5. Or this is 2 and 1/2. In other words, it's between 2 and 3. It's a little bigger than 2, but not quite 3. Well, this makes the ordering much easier for the right-hand side, right? So I see that 3/4 is between 0 and 1. 1 and 2/3 is between 1 and 2. And 5/2, which I can also think of as 2.5, is between 2 and 3. On the other side, since these are negatives, note that these are just the opposites of the ones we've just been working with. The order is reversed, right? The same way that if I have $10 in my pocket, I have more money than if I have $5 in my pocket. My net worth is greater with the $10 in my pocket than with the 5. But if I owe somebody $10, I have less money than if I only owe them 5. So on the negative side of things, the ordering is kind of reversed of what we might expect. In other words, the negative 5/2 falls between -3 and -2. The negative 1 and 2/3 falls between -2 and -1. And the -3/4 falls between -1 and 0. Or if we were to draw this on a number line, I think I actually need a little more room than that. Let's put 0 here. And we have what? 1, 2, and 3. -1, -2, and -3. So I know 3/4 is between 0 and 1. That's what I had set up here. So it's somewhere in this interval. I could just kind of put it maybe in the middle of the interval, but I probably could do a little better than that, right? I'm never going to be super accurate when graphing on a number line like this, but I do know that 3/4, there's 1, there's 2, there's 3, and it looks like I have more than a half, right? It looks like it's going to be closer to 1 than it is to 0. So maybe I'll put it a little bit closer to 1 than to 0. So this is 3/4. And even being careful, it's still trying to make my 4 into a 9. Similarly, with 1 and 2/3, I have 1 whole unit plus 2/3. Well, 2/3 is more than a half. So I'll put this a little closer to 2 than to 1. And then 5/2 or 2.5 is right smack between 2 and 3. So I'll put that right in the middle. 5/2. On the other side, I kind of mirror things, right? -3/4 the opposite of 3/4 just flips over 0. It's going to be a little closer to -1 than it is to 0, but it's going to be between -1 and 0. -1 2/3, the opposite of 1 2/3. 1 2/3 is a little closer to 2 than it is to 1. -1 2/3 is going to be a little closer to -2 than it is to -1. -1 2/3. 5/2 is right between 2 and 3. -5/2 is going to be right between -3 and -2. And you wouldn't need to color code these usually, but I just color coded them to keep straight which ones we were talking about. So this would be the ordering and their placement on the number line. And again, in this context, thinking of 5/2 as a mixed number made a lot more sense. If we were, say, adding or subtracting fractions, or certainly multiplying or dividing, then probably thinking of, say, 1 2/3 as an improper fraction would make things go a little more smoothly. Any questions on anything from today? All right, so I think instead of starting 4-2, since this was a lot of material, a lot of different ideas, and since we also have the exam this week, I think I want to stop there. This is, was kind of an introduction to fractions. Again, strongly recommend you take the exam, today if at all possible. And then that gives you a nice buffer if anything does go wrong. And I do strongly recommend, like I said, just touching base with fractions a couple of times a day, every day for, the next couple of weeks. And it's just a lot easier to do a couple problems here and there. And take this in little chunks, because I know a lot of folks struggle with fractions, really don't like the idea. But if you take it in little chunks, it's much more manageable and you learn a lot better than if you try to like push it off and procrastinate and wait till the last minute and then try to do a whole big session all at once. That's number one, just not really fun to do that. And number two, it's more frustrating because if you're getting something wrong, you're up against a deadline for the homework to be turned in or something. Then it's just more stressful to figure out why is this going wrong, instead of being able to either send me an email or have the time to go back to the book, or just have the time to sleep on it. Just put it down for the day, come back to it the next day, and sometimes you get a breakthrough. It's like, oh yeah, that's so clear that now that I've had a break from it, I'm not so close to the problem. Okay, so we will stop the recording.